Hi, welcome to the analysis of gain and phase margin, that is the stability in control systems. Okay, first we'll just define what is this phase margin. So before we define phase margin, let us try to understand this gain crossover frequency. Gain crossover frequency is that frequency at which magnitude of the open loop transfer function is unity. So it is that frequency at which the magnitude of the open loop transfer function is 1. Then once we know what is the gain crossover frequency, it is that frequency where the magnitude plot crosses 0 dB line or unity line. Next what we have is how do we define this phase margin. Phase margin is, of course, if I just read out what is there in the definition, phase margin is that amount of additional phase lag at the gain crossover frequency required to bring the system to the verge of instability. So assume that at the frequency of omega GC, you have a phase of around, assume that it is around minus 100 degrees. So if it is at minus 100 degrees, now we know that for the system to be unstable, the phase should be at minus 180 degree. If phase at omega GC is minus 100 degree, I need to add another minus 80 degree, that is additional phase lag that should be added is minus 80 degree to make that minus 100 as minus 180 degree. So meaning to say, so it is the additional phase lag at the gain crossover frequency that need to be added to make the system at the verge of instability. How do we actually find that phase margin is? So the phase margin can be found, that is 180 degree plus the phase angle phi at of the open loop transfer function at omega equal to omega GC. So this is the definition of PM. That is phase margin is 180 degree plus the phase of the system at omega is equal to gain crossover frequency at omega equal to omega GC. So this is how we can find the phase margin. Similarly, gain margin. So before we define the gain margin, so let us try to understand the phase crossover frequency. It is that frequency of the open loop transfer function at which the phase of the open loop transfer function becomes minus 180 degree. This is actually minus 180 degree. Let me slightly modify. Phase crossover frequency is the phase at which the phase angle of open loop transfer function is equal to minus 180 degree. So once we know what is that frequency at which phase is minus 180 degree, then gain margin is defined as the gain margin is the reciprocal of the magnitude of the open loop transfer function at the frequency at which phase is minus 180 degree. That is, phase margin, the gain margin GM is defined as reciprocal, that is 1 over the magnitude of the open loop transfer function with omega equal to omega PC. You can see we are replacing omega by omega PC. So reciprocal of the magnitude is reciprocal of the magnitude at phase crossover frequency is the gain margin. And again, gain margin can also be defined in terms of dB, which is minus 20 log of again the magnitude at omega equal to omega PC. This is how do we actually find the gain and phase margins from the Bode plot. So assume that now this is the magnitude plot of the Bode plot. So this is the phase plot of it. Now if you can see this what we define as omega GC, that is gain crossover frequency. You can see this is 0 dB. This is magnitude plot. Whenever magnitude becomes 0 dB, that is equal to 1. This corresponds to omega GC. So at that particular phase, at that particular frequency, whatever is the phase you have, so since it is 180 minus this, so this much difference is actually the phase margin. Since phase margin is positive, here it is positive, we are going to define this as a positive phase margin. Similarly, to find the gain margin, so this happens to be minus 180 degree line, and the corresponding frequency is omega PC, that is phase crossover frequency, and you will going to have certain magnitude of this magnitude plot. You can see this magnitude is always negative dBs. So if you can actually find what is the gain margin of this, since it is negative of the magnitude, so that's why this gain margin is positive. or if you take this in terms of ratio, this will be less than 1. Whenever I take it reciprocal of that, then the gain margin happens to be more than 1. This is how the typical Bode plot of a positive gain margin and positive phase margin look like. One thing you can observe for a positive gain margin and positive phase margin, the gain crossover frequency will be earlier to the phase crossover frequency. You can see this is omega GC. You have omega PC here. Omega GC comes earlier to omega PC here. So that is a typical range of frequencies, the comparison of omega GC and omega PC. If omega GC is lesser than omega PC, for a typical system, you're going to have the system is stable. And you can see this is an unstable system where you have the gain and phase margin from the Bode plot. Now you can see again, now this is omega PC, that is phase crossover frequency where the phase is minus 180 degree. This is gain crossover frequency when gain is 0 dB. Just come down here, and whatever is the phase, you can see it's always more than minus 180. So when I say more than minus 180, it is like, okay, minus 190, minus 200, minus 220. So since it is 180 plus this angle, so if it is minus 200, then the phase angle, then the phase margin is 180 plus of minus 200, which happens to be minus 20 degree. So that's why the phase margin is negative here. Similarly, you can see this is omega PC. So the magnitude is always more than, it's always positive. When I say the gain margin is negative of the magnitude over here, so naturally the gain margin is negative. So this way, here you can notice the omega PC is coming earlier compared to omega GC. So this is typically how does an unstable system will look like. This is a comparison between the stable and unstable system. So this is the magnitude phase plot. Omega GC is coming earlier to omega PC, but here you can see omega PC is coming earlier to omega GC. So this is a negative phase and gain margins. This is a positive gain and phase margins. Similarly, we can find the gain and phase margins using Nyquist plot also. We know that this whatever magnitude you have, this happens to be 1 over the phase margin. So in order to find the phase margin, assume that if this is equal to 0.2, then the gain margin is 1 over 0.2. So you can see this is that minus 1 plus J0 point, so which corresponds to GH plane or GH plane, G into H plane. And you can see this is a unity circle. So this is a magnitude corresponding to 1. The phase angle at which the magnitude is 1, this corresponds to the phase which corresponds to magnitude of 1. So 180 degree minus of that phase. So you can see this gamma is actually the positive phase margin. And similarly, this is again, this is also more than 1. This is also positive. We want to have a positive gain margin, phase margin. System will be stable. If you just see here, you can see the phase at omega GC happens to be more than minus 180. So that's why the phase margin is actually negative. So here you can see, suppose if you actually find this angle, so this angle is something like, okay, minus 200 or minus 220. So when it is minus 220, the phase margin is actually 180 minus of this, which is actually this, which is negative now. So, and again the gain margin, if you can see here, this is gain margin. So since it is more than 1 the magnitude, so gain margin is usually negative. So in terms of dBs, this will be a negative gain margin. So, and you can also notice that this minus 1 will be encircled by this contour in GH plane. So that's why the system will be unstable. So this is just comparison. You can see this is not encircling minus 1 plus J0, so that's why the system is stable. But here you can see it is been encircled by this contour is actually encircling minus 1 plus J0 point. The system is unstable here. Okay, for defining the system stability, it is not simply possible by just knowing the phase margin and gain margin. So it is necessary to know both the gain and phase margin to know the relative stability of the system. If both phase and gain margins are positive, then we say system is stable. If both are negative, then we say it's a negative, it's an unstable system, or the system is instable. It just indicates the instability of the system. Okay, this is the typical values of gain margin and phase margin. For a satisfactory performance, we are looking at a phase margin of around 30 degree to 60 degree, and the gain margin should be always greater than 6 dBs, so that the system is guaranteed to be stable even when you close the system, even upon the closure of the system. And of course, this will have a better time constant in terms of time response of the system. So let us take some examples to identify, okay, how do we find out the gain margin, phase margin of a system. So here, this is the first transfer function having a pole at the origin, and you have two poles, one at 100 and the other is at 10, which is on the left hand side. So as we know that the gain margin is 1 over the magnitude at omega pc, or negative of the magnitude in terms of dB. The phase margin is 180 degree plus the phase at omega gc, the phase at omega gc. For this particular transfer function, we will write the magnitude equation and phase equation. Of course, by equating this entire thing to 1, we will get omega gc. So that corresponds to 7.84 radian per second. We can see if you equate this to minus 180 degree, we will get omega pc, that is the frequency at which the phase becomes minus 180 degree, will be 31.62. If you can notice, this omega gc is coming earlier to omega pc. The system has to be stable system. Let us see what is gain margin, phase margin. So as we know that the magnitude at omega equal to omega pc is 0.09, which will going to give a gain margin of 1 over this quantity, which is 11 now. In terms of dBs, it will be 20.8 dB. You can see it is positive, and we know that the phase of the system at, okay, how do we define the phase at omega equal to omega gc? So phase at omega gc, in this phase equation will substitute omega as omega gc value. We will get a phase of minus 132.5 degrees. The phase margin now is 180 degree plus the phase at gain crossover frequency. This happens to be 47.5 degrees. So the gain margin is 20.8 and the phase margin is 47.5. The system is stable. We will just have a look at the 20 sim simulator for this particular example and try to see whether we are getting the same gain and phase margins. Okay, let us edit the poles and zeros here. Of course, it's already edited. You can see one of the pole is at origin, the other pole is at minus 10, the third pole is at minus 100. Of course, we are setting the system gain as 10, so that's what is given here. So we are supposed to have a system gain of 10. You can see the system gain, what we are expecting is okay, this is the system gain. So let me just, okay, the system looking at is 10. So this is, since it is in time constant form, this happens to be the system gain, which is 10. So that's what we edited here. So this is the system gain having a system gain of 10. The poles, 3 poles are at 0, minus 10 and minus 100. So let me just apply this and then try to see what is the Bode plot of it. So let us see the Bode plot, and we can see here the phase, this is gain crossover frequency, which is 7.8. So that's what we got here as so we got, this is, you can see 7.84 is the omega gc, and omega pc is 31.62. Let us see what is omega pc. You can see this is 31.62. It is the frequency at which phase is minus 180 degree. So this is phase of minus 180 degree. The corresponding frequency is 31.62, and corresponding to this, we have a phase margin of 47.39 degrees, and corresponding to this frequency, we have a gain margin of 11. So that's what we specified here. So we are getting a gain margin of around 11 and a phase margin of 47.5, which is here in your plot also. You can see it is gain margin is 11. This is around 47.3. So this is what we got here. We got 47.5, which is almost there in the plot also. So in the plot we have it as almost close to. So the plot